Yesterday we saw expectation, and that basically was average. Variance is to do with the other statistical piece of data that you use, which is standard deviation. Now, variance is not standard deviation. We'll come to that as we go through this, but it relates to the spread of the data. So, all right, we've got our discrete. So basically what we're looking at in this topic is just discrete ones. We'll worry about continuous ones later. So for discrete random variables, the variance is given by this. Okay, the sum of, now this time, remember, expectation was x times px. This time it's x minus mu, so the average, all squared times px. And once again, yes, probability has to be greater than or equal to 0. Mu represents the expected value of x. Now, x minus u is what we call the deviation, not the standard deviation, but the deviation. So sometimes you get positive numbers, sometimes you get negative numbers, depending on whether it's above or below. That's why in the formula we square it. So that way they always become positive numbers. And variance is, as I was saying, it's a measure of how spread out the data is. All right, let's go back to the same one we did yesterday, the milk marketing survey, and we're going to find the variance now. Okay, you'll recall we had our table like this yesterday, and we found out that expected value was 2.2. So that 2.2 is the expected value of x, or the average, whatever you want to call it. We're now going to need another row. We're going to have to work out what x minus mu all squared is, because we're going to need that in our formula. So basically, whatever the x value is, subtract the average, 2.2, square it, although I've written it as a fraction. Okay. You'll notice I haven't bothered finding the sum, because that by itself doesn't really tell me anything, so I don't worry about that total, because now I'm going to get those numbers and multiply all of them by the probability. That's what we're interested in. So if I multiply those all by the probability, add them up, I get 1.52. And so there's our variance. Now, look, there is an easier way, to be honest with you. I mean, that's the technical formula for it, and it works and it's fine. But geez, trying to remember all that can be tricky. There's a much simpler way of remembering it, and it comes up quite nicely. You see, look, this is our variance. It's the sum of x minus mu all squared times px. Now, if I was to look at that, I could say that's the same as the expected value of x minus mu squared. So remember, the expected value was x times probability of x. So this is x minus mu squared times the probability of x, so it's the expected value of x minus mu squared. Now, x minus mu squared I can expand out. That would be x squared minus 2 mu x plus mu squared. But one of our rules for expected value is we could do each bit individually. So it's the expected value of x squared minus 2 mu times the expected value of x plus mu squared, because mu squared is a constant. So if I say, what's the expected value of a constant? Well, it's got to be the constant. What else could it be? So that's just mu squared. But now that middle one, expected value of x, you remember we defined to be mu. So it's actually minus 2 mu times mu. So now we have expected value of x squared minus the average squared. And that's a quicker way of working it out. So expected value of x squared will simply be the sum of x squared times the probability of x. So now when we do our table of values, it's a lot quicker because I know I'll have a probability row. I'll have xpx, so I can do expected value. That's mu, remember, 2.2. But now the next row is just x squared px. That's the other one. So I'm just multiplying by x again. So I think it just makes it simpler. We multiply by x again. That's 6.36. So that is the expected value of x squared. So to work out the variance, the expected value of x squared minus the average squared. And there it is, 1.52. That's it. I think that's the best way of doing it. So what is standard deviation then? Remember I said x minus mu is deviation. But we square it because we want it to be positive. So what that basically means is, this variance we've just worked out, whatever the units are, must be units squared, because we squared it. But if I want to talk about the spread of the data, I don't want units squared. I just want units. So all the standard deviation is the square root of the variance. And then it brings it back to units rather than units squared. So standard deviation is just the square root of variance. Now, if I remember correctly, in junior school you get told this wonderful formula to work out standard deviation. No one can ever remember it. And you go, oh God, how do we work out standard deviation? Well, this is a much neater way of working out standard deviation. It's very simple. We multiply by x to get expected value, multiply by x squared, we've now got that one. Expected value of x squared minus the average squared, bingo, square root it, you got the standard deviation. So another way of thinking about it is sigma squared is variance x. In fact, you might even see that symbol used for variance, sigma squared, because sigma, the little sigma, is the symbol for standard deviation. So for ours, it'll be the square root of 1.52, so around about 1.23. Let's just talk a bit about standardising data then. Why not? That's when we want to compare sets of data. It's like if I wanted to compare your maths results to your English results, I mean, using the raw marks really tells me nothing because they're totally different tests. There's no reason why they would be the same averages and things like that. So standardising data brings it back. So the averages are the same, the spread's the same, and we can make a reasonable comparison. So the original data, we're saying the expected value of x is equal to mu and the variance is going to be sigma squared. That's our original raw data. This is what some subjects do, people who don't understand mathematics. I don't know if any of your teachers have ever done this. They get the results, they're not happy with the results, so they say, oh, well, it's all right, we'll just add 5 to everyone's mark, and then that'll make the average better. Well, let me show you why this is not a great idea. Okay, so we're now going to introduce a new random variable. I'm going to call it y, and y will simply be x plus a constant. So we're going to add this constant to every piece of data. So what's going to happen to our expected value? The expected value of y will be the expected value of x plus c, but we can treat those separately. And of course, expected value of a constant is a constant. We know the expected value is the average. So yeah, okay, we achieve what we wanted to do. We lift the average. It's now whatever the original average was plus the constant that we've added on to everyone's mark. Fantastic. What happens to the variance though? So the variance of y will become the variance of x plus c. Well, what was variance? Oh, that's right, we said we're going to make it the expected value of x plus c squared minus the average squared. Expand out x plus c squared, okay, x squared plus 2cx plus c squared. Expected value of x squared plus 2c times the expected value of x plus the constant squared minus all that. And eventually, here we are, expected value of x squared minus, well, hang on, does absolutely nothing to the spread of the data. I've ended up with exactly the same thing. The expected value of x squared minus mu squared. See, effectively, what you've done is just shifted the curve. That's all you've really done. Where's a picture? There you go. That was the original data. What have we done? We just added a constant number to every piece of data. So, bing, we just shifted it along. The spread of the results is still exactly the same as they were. Not a great way of doing it. Don't know if anyone would ever do this, but just say, they went, oh, I'll tell you what we're going to do. Maybe the marks are too high. So we're going to divide every mark by the same amount. What would happen there? So the expected value of z would be the expected value of x over k. The variance would be the variance of x over k. Well, expected value of x divided by what's a constant, so that'll be constant. We'll get the average divided by k. Makes sense. We're going to divide every mark or every piece of data by k. Then the average will end up being divided by k. Yeah, makes sense. What happens to the variance? Okay, we end up with the expected value of x on k squared minus mu on k squared. Playing around with this one, we've got a common denominator of k squared. And on the top, hang on a sec. On the top, that's what we had as the original variance. So the new standard deviation has also been divided by k. See, you end up with sigma on k, all of it squared was the variance. So what does it do? It has changed the shape of the data. There's the original data. We're dividing by k. I'm assuming k is a number bigger than 1 here, so the number is smaller, mu on k. But it squeezes the spread in now because the spread now is going to be smaller. And so it's actually being pushed in. We use z-scores. It's a far more efficient way of standardising. The attempt is what's called normalising the data, and next year when we look at our stats we'll talk about normal distributions and things like this. There's the formula for it. It's a very simple formula. Every piece of data, all we're going to do is we're going to subtract the average from everyone, and then we'll divide by the standard deviation. So it sort of combines those two ideas together. What's going to happen to this new piece of information? So it's the expected value of x minus mu on the deviation. Well, deviation, that's a constant number. So I get expected value of x minus mu on the deviation. I can split that up. Look what happens. The average becomes 0. So the average for all these standardised z-scores will always be 0. The variance. So variance of x minus mu on sigma, it ends up being 1. Because we end up with the variance of x minus mu. But remember we saw when we shifted it, it didn't change the deviation at all, so I still have sigma squared on sigma squared, which is 1. So it's beautiful, because everything then just has a standard deviation of 1, an average of 0. Makes it very easy to handle the data. All right, just thought I'd talk about that. I don't know that we really need to know that for this one we're about to do, but that's where z-scores come from, and that's why we do it. So 13C we'll add to our list of questions to look at.